All right, so we're live. Hello, everyone.
Hello.
Good day, good afternoon, good evening. We are here in northern Denmark, so it's good afternoon for us. Such a pleasure to be here for our webinar. I'm going to put some slides just to help us visualizing a little bit what we have to say here today. So I hope you can see our screen. So welcome. Today we're going to talk about realizing the first standardized 5G new radio NTN solution. Um, so we've been very excited to talk a little bit more about that on the technical side as well. Also, how to take some initial steps as well to visualize how to actually go into new radio NTN. Um, so yes, so let us introduce ourselves. So I'm Rafaela. Nice to meet you all. I'm from the commercial team here at Gatehouse Satcom. Um, and this is, yeah.
And I'm René Brandbo Sørensen. I'm a research engineer here at the Gatehouse Satcom for almost 3 years now, doing delegation work in 3GPP, among many other hats that I wear.
Yes, precisely. And today, taking some time to here to have a discussion with us. So this is the agenda for today. How it's going to go down. Let's say. So this is the welcome that we're doing now. So you know a little bit who we are. And then I'm just going to talk a little bit, very brief, about the significance of 5G new radio NTN. Remember a little bit of the use cases, not very much in depth, because our intention is to go a little bit more into the technical one, but also just dip in the toast. It's a lot to uncover. And then Renee will go a little bit more into exploring some key features, talking a little bit more about the technical challenges, and then at the end we're going to have a live Q&A session. So you're welcome to send your questions throughout the presentation. We're going to look at them afterwards and try to answer as many as we can. But in case we do not make it to answer all of them, we're going to send all the answered questions through email together with the recording of this webinar. So all of you who signed up will get this on email. So don't worry, make as many questions as you want. We'll be happy to look into them. So this is us. This is just a second. Yeah, this is us, Gatehouse Satcom. We are a satellite communications software dedicated company, meaning our expertise and what we do for around 25 years is software. And for Satcom, we have a very vast and solid experience with more than 15 different waveforms, developing from scratch, doing test tools, testing in many areas. So as a part of our own development as a company, but also as the market development, we joined the 3GPP group that Renee mentioned that he participates on. And 3GPP is an organization that defines the standards for mobile communications. So we contribute to the definition of the standards. Renee himself, he was in Chicago a couple of weeks ago. So based on our legacy in Gatehouse, of all of our work with Satcom, and also as a part of developing our solutions, looking into 3GPP, we're able also to operate throughout the entire roadmap, let's say, of 5G NTN. So from planning, designing, doing demonstration, and then also deploying the solution together with customers. So let's go a little bit about the significance that I mentioned. I'm just going to be quite brief. So 5G in total offered us some groundbreaking capabilities as well in mobile communications as a whole. But for us to see this to come in full fruition, let's say, 3GPP started developing the new radio access technology, which is the 5G new radio NTN. What does that mean for us from the NTN side of the story, which is most of us here today, right? We're from the Satcom part. That means that we see a little bit of a shift in the nature of our technologies that first was mostly standalone proprietary technologies, so everybody working on their own, and then a shift into going to standardized technologies. So meaning we all can collaborate and work together. So that means in terms of in total in mobile communication, it means that we see a unification of NTN, so non-terrestrial and terrestrial networks, and that gives us access to the mass markets. Let's say, does that mean that the NTN industry will compete with the terrestrial one? That's not the what is envisioned. The envision is to the NTN technologies to be a complement to the terrestrial ones. So the key word for us is collaboration. So we're going to see the NTN players collaborating with the TN ones, and then all of us collaborating with the chipset manufacturers, with the mobile network operators, hardware, you name it. So yeah, some use cases. I'll go very brief because we actually had an earlier webinar talking about this, so you can search my website and afterwards. So yeah, some use cases that we know, and this is how we're going to complement, right? So in smart cities, um, applications, let's say, NTN can work as a backup, so it makes the applications, the whole system, more resilient, more trustworthy. So in case there's some failures in the terrestrial network, the NTN is able to pick up there and don't let it fail as in total. It can also work for data collection for remote areas. So let's say for industrial automation, it can work in places where the terrestrial networks cannot go. So let's say mines, offshore networks, forests. The NTN could be there. 5G new radio could be there. And in terms of augmented reality, uh, and AI, which is the talk of the entire world right now as well, it can offer a little bit more power and open doors for new applications that requires some global connectivity. So that could be tourism, telemedicine, disaster relief, you name it. But as we all know, for 5G in general, it is the case also for the NTN side. We have a road of an evolution of the technology to happen. So, and that comes with some challenges we see, and then us together, all of us together, solving and getting into the what is meant to be. So, let's see a little bit more, Renee, of yeah, some of the technical parts.
Yeah, all right. So speaking of use cases, I'll start by going a little bit into ITU's vision for the satellite component of IMT 2020 and translate it. That means what is the 5G satellite requirements that were put out from the beginning, or the target requirements. Use case wise, there are these three pillars: enhanced mobile broadband, massive machine type communications, which we recognize from the terrestrial world if we have been there. One providing mobile broadband and one providing coverage for many, many devices. These have been taken directly to the satellite world. But the third case, which on the ground has been called ultra reliable low latency communication, has been renamed and relaxed a lot the constraints, especially for latency, renamed to high reliability communications for satellite. And that's, of course, due to the propagation time being involved in satellites so far away from Earth. You can never obtain the very low latency or the ultra low latency part of UILLC. On the left-hand figure in this slide, you cannot see the three different pillars or unity vectors of service, which then have different KPIs associated with them, and they have different priorities. So NR NTN is meant to serve the enhanced mobile broadband and the high reliability communication use cases. So for all the KPIs, it should be able to deliver service with a high priority, except the connection density KPI, which is delivered by the IoT NTN standards. On the next slide, we can see the requirements put out by ITU in the table, and I just want to highlight for EMBB, they all relate to terrestrial 5G. Just want to highlight for EMBB, we see a peak fire rate, a requirement of a peak fire rate of 70 megabits per second, and experienced data rate, users experienced data rate of 1 megabit per second in the downlink. And in the uplink, similarly, we have 2 megabits per second physical peak rate and an experienced data rate of 100 kilobits per second. So this is far from what we're used to in our everyday life with our cell phones, terrestrial networks, but it is a large step forward for direct-to-device from satellite. Then you have the high reliability communications, HRC. The main requirement here being that you only have one failure in 1,000 transmissions that you're doing, which is quite reliable. And then, of course, MMTC has a low device density compared to terrestrial networks. So we see in the requirements, it's 3 devices per square kilometer per NB-IoT carrier, for example, NB-IoT channel. But because the coverage area is so large, both for NR NTN and for IoT NTN, due to the satellite cells, this adds up to a lot of devices in the end.
Okay, yeah.
So, yeah, I think that's it for the requirements. So I wanted to talk a little bit about the timeline of 3GPP, and then I'll go a little into the architecture for next generation RAN, or basically the NR architecture, and how NTN fits in there. And I'll go back to 3GPP and the features that have actually been defined. But the basic timeline of 3GPP here for NTN has been that before release 17, so in release 15 and 16, there were studies, as indicated on the figure here. This might be too small for you to read, certainly is for me. 38.8.11 and 38.8.21 were taken on in release 15 and 16 respectively to find solutions for supporting NR NTN or NTN in NR. Then in release 17, these studies were made reality with the specification into NR of various solutions for how to solve these different technical problems you have when you go to NTN with your terrestrial network. The studies mentioned here are the RAN studies, by the way. There were, of course, also studies in SA, the System Architecture Group, and in CT. So looking a little bit forward, release 18, which we are about to finish in the spring, summer next year. There are coming more enhancements for NTN, and looking even more forward in release 19, there will be some further enhancements, which every step is making it more reliable, making it work better with the NTN network, which, as you mentioned, is important in interoperability. So this we are going to see, and one exciting thing that's going on now in December of this year is the submission of the self-evaluation that 3GPP has been undertaking this year during release 18 to submit the NTN standards from 3GPP to ITU, and say they fulfill the requirements that we just talked about. Nice. So that's going to be...
It's a big date coming.
It is. We are crossing our fingers, dotting our I's and so on, right? That's very exciting. But I'll get back to what's in release 17, 18, and what we see might be coming in release 19. For now, let's discuss a little bit the architecture.
Yeah, I have a little question. How long does it take usually from when you start to work in, let's say, release 17 until you submit to ITU?
Oh, well, that's a very good question. So here it has taken many years. The way from the end of one release to the end or the release of the next one, next version, is 2 years usually. And this, or NTN, has been going on for several releases, right?
Yeah.
So you have to think already from release 17, you have to think 6 years back at a minimum.
Oh, wow.
Yes.
Yeah, a lot of work.
Yeah, and before that, there were also people doing work. So
yeah. A lot of work, a lot of brains. All right.
Okay, so I wanted to start off discussing the architecture for new radio and next generation radio access networks. For the terrestrial component first. Very basically, the connection from the UE to the base station is what we call new radio. It's the new radio waveform. Then the GNB is, or the base station is connected to the 5G core, for example, the AMF in the control plane part. And this connection is called Next Generation Access Protocol, AP. So the role of new radio is to create what is called radio bearers. So you have the waveform stack going from PHY, MAC, RLC, PDSP, RC layers, and on top you can then transmit. So that is what makes up a radio bearer. On top of this radio bearer, you can then transmit more protocols, because that's what we engineers do, right? We put more protocols on top. But these protocols are then called non-access stratum NAS protocols. Okay. And these are the communication. This is the communication that the UE is doing to the core. So the new radio is used to connect to a base station. Then the base station forwards the information that was transmitted on top of the radio bearer to the core network. Okay. And this is, for example, mobility management, which is used to identify where the UE is in the world. Yeah, and then on the right hand of this slide, I have a figure showing a little more on the core side, where everything on the very bottom is called lower layers. That is all of NR, all of the RAN. On top of that, you have the basic NAS layer, which is mobility management, and then you can run session management, UE policies, SMS service, location services on top of that. So these are the more network-oriented things, which we are not very much into that. So I will stop speaking too much about it. We're on the NR side of things. Yeah. But it's interesting to know this because, of course, when you're adapting the entire architecture for NTN, you don't just have to adapt the RAN part. You have to adapt the orchestration and management, operation and management part, and the network core.
Okay. Yeah.
So
all interconnected.
It's all interconnected, exactly. So in the next slide, we have a depiction of a transparent and regenerative satellite access node. On the top figure, I have taken the stack that I was showing before, and then I have inserted into it our non-terrestrial component. So there's a gateway and there's a satellite. Now, the gateway and satellite can be located between the base station and the UE. So the thing that's transmitted all the way across this link is the NR interface. It's the NR waveform. This is called the transparent architecture. In this architecture, the gateway is forwarding NR to the satellite access node, and the satellite access node is forwarding NR to the UE, and then all the way in the reverse direction back to the base station.
I see.
Then there's a regenerative option where you have taken the base station and put it onto the satellite access node. So now, instead of having NR on the link between the gateway and the satellite access node, we have this next generation access protocol. So the feeder link has turned into a core network link, backhaul link, more reminiscent of a backhaul link. Okay. Yeah, in the release 17 standard, the transparent satellite access node is what has been standardized. But to the best of our knowledge, there is absolutely nothing stopping you from creating a regenerative NodeB, putting it on a satellite, launching it. It should work for commercial networks all the same.
Nice. So that means that the NodeB on the transparent goes into the ground, and the regenerative, it goes into the satellite.
Yeah. So the NodeB is on the ground in the transparent use case, and it's within the satellite in the regenerative case. Of course, you can have middle things in between where you have parts of the GNB on the satellite and so on.
Okay.
According to different splits of the protocol stack. But that's a little more advanced than we're going to go into today. So some key adaptations to make this work in this architecture work in NR has been that the UE to the satellite link must compensate for the movement of the satellite, no matter which architecture you have, right? And there will be a delay towards the satellite. And then in case of the transparent payload, there will be a delay after that towards the gateway and the base station. So the frequency must be compensated, of course, and then the delay must be compensated towards the satellite for your physical waveform. And then when you're waiting for response, you will need to adjust all of those timers according to the full delay of the exchange round trip time. So there are timer adjustments. Then the HARC and the random access procedures have had to be redesigned. These are procedures which are handshake procedures. So they were designed for very low latency. Sorry, a little bit. With longer round trip times, they don't work the same. So there's been some redesign there. I'll get back to that. And then, of course, there's the mobility, because now you have base stations which are flying around, moving. And conventionally in terrestrial cellular, you have a fixed base station, of course. So the UE knows if it finds a good cell to camp on, then I'm in that cell, and I can count on being at that cell if I wake up in a little bit again. Of course, the UE can move, but then it's not going to move that far, and so on. So you have to think very differently about the tracking in some cases. Yes. So the release 17 features, part of them are addressing all these requirements, as I just said. Then there's what I would call optimizations on the hard front. A little more was done than was needed, which is just good. And then a bunch of the NR features we all know and love from terrestrial were extended to work also for NTN. So having conditional handovers, for example, it's a very cool feature because of the satellites moving. Moving away from the UE, then the UE can have a conditional handover set up, so it knows to go to the next satellite, and it can do so immediately because they made the feature so that you can give the information about where's the next satellite.
Okay.
So all very cool stuff.
Next one.
Yes. Then I'm going to go a bit more into release 17 before I tell you the overview of the features of release 18 and 19 also. In release 17, there's been some changes to the GNB stack. I tried to make a figure here, which is very rough, but I think it gets the point across that you have changes all throughout the stack, but primarily it's in the PHY, MAC, and RRC parts of the stack. So RRC and PDSP, not so much. SDAP, not so much. But yeah, as I said before, time alignments, random access, HARC, and this timing alignment in PHY have been some of the bigger ones, lower in the stack, and at the very top in IRC, the control information layer. There's been introduced new system information blocks to tell of the position of the satellite. At this point, I think everyone knows it because it's been a while since that was defined, and we have so many webinars. It's been mentioned everywhere. They're tracking area list, cell bar, bits. So a bunch of control information there. And then, of course, as I said, these handovers, which are very convenient. It can be very convenient. Then there's a little more an entirely new thing for the operation and management part, where this system information that the satellite is broadcasting constantly, saying, this is me, this is where I am, this is the delays that you should account for. This information, where does it come from? Well, the answer comes from a new block, operation and management, which is the responsibility of the satellite mission NTN operators to have and transmit to the satellite. And of course, in the case of regenerative, you wouldn't transmit the location of the satellite to the satellite. You'd probably have a GNSS on board, and then it would be able to calculate a lot of this on its own. Yeah. But there are some new functions here that everybody will have to think of.
Yeah, nice.
Yeah, I think that's good. So I'll go very quickly over these. I put up 3 of the key adaptations for NTN in the radio layer in release 17. The first one being the time and frequency synchronization. So what is done here is the UE will have a GNSS on board. So the UE will know exactly where is its own position, or maybe it has been provisioned with its position and it's fixed in the same place forever.
Okay. Depends on what they choose, like their needs and requirements.
But in general, let's say they all have the GNSS. And then the satellite access node or the base station is transmitting the SIP19, including the ephemeris, which is the location and speed, the position and movement vectors, for example, or orbital parameters of the satellite access node.
Okay.
That means the UE can estimate what is this relative speed between the two and what is the Doppler then that it should compensate on the frequency part, and it can of course calculate the time to the satellite. Then the satellite also has to transmit NTA common, which is the time on the feeder link towards the gateway. This is always, you can just put it 0 if you put the base station on the satellite access node, but if you choose to put the base station in the transparent architecture, then you need to put the NTA common. Yes, and then you adjust your scheduling delays also according to zip19. So that's the first major adaptation. Next major adaptation is for the handshaking procedures. As I mentioned, the HARC and the random access. Here, the random access is maybe the easiest to understand. When I transmit a preamble saying here I am, the base station will transmit a response saying I heard you, or maybe asking who are you is a better analogy. And the UE would respond, well, I am this UE.
So this exchange of communication is the handshake.
Yeah. Whenever you have an exchange of communication like that, it's called a handshake.
Nice.
So the window of time that the UE would wait to get a response back after saying here I am has been increased. Okay. It's very simple. You have to increase it because, again, satellites are far away. Propagation distance, propagation time has been increased. Now, the HARC procedure is automatic hybrid automatic repeat requests, I think. Procedure is for the file layer. Every time you're transmitting a transport block, which is the minimum, let's call it a logical unit of bits. I'm transmitting a block of bits to you. Then you look at the block of bits and you see in the last row, they don't look like they're supposed to give you a code word, but it's not the correct code word. So you transmit back to me a NAC saying, no, it wasn't correct. Then I know I'll have to transmit the block again. Mm-hmm. In NR, you can do that for up to 16 blocks in parallel. So I can transmit 16 blocks to you, and you can, for each of them, tell me if they were okay, nice. Or not. Sorry. And then for NTN, this process is going to take a long time, right? Because I have to wait. Every time I'm transmitting to you, I have to wait for your response. Exactly. Every time you're transmitting to me, you have to wait for my response. That's stalling the throughput of the network completely, especially for geo. So what was introduced was an increase in the number of HARC processes. This is useful if you want the reliability still of having the check, but you want to have a larger throughput because you can transmit more blocks, and then you'll still have a good turnaround in the acknowledgements on the blocks. And the other feature is disabling HARC, which is coming for IoT NTN in release 18 as well. Nice. Disabling the HARC means I don't care if you got it or not. I'll just try to transmit it with modulation encoding that is so low from the beginning that you will very likely get it no matter what. Okay. This is more reminiscent of satellite communication in general, or normal conventional satellite communication.
So instead, you just said like, here's the block.
Yes, and you try to do it with such high reliability. In terrestrial communications, it's fine to fail. You use a blocker rate of maybe up to 10%, right? where in satellite communications, you might use a 1% block error rate. Right? You don't want to have your blocks fail in satellite communication because it takes so long time to exchange the blocks.
Oh, I see.
But the paradigm depends on what orbit you're using and so on. It's maybe changing a little bit because we're going more to LEO. Yes.
Nice.
But that was the second feature. Let me be more quick on the third one, mobility. Celery selection, of course, has to be revamped for NTN. That is more into the UE behavior that is into the base station. Handovers in NTN have been designed so you can do it with NTN cells properly. Conditional handovers. We have information in SIP19 not only about the cell that is serving you, but also about neighboring cells and which frequency they're using. There is the tracking of NTNs, of UEs in NTN, which is the core part. I was mentioning all the way in the architecture you have changes, right? This is within the core part. The core will need to keep track of the position of the UE, at least to the level of which tracking area it is in. And this is different from terrestrial networks, of course, because you have these moving satellites. Yeah, I already mentioned this. Course location information can now be sent from the UE. So a GPS signal, if your UE allows this, can be transmitted a GPS location, GNSS location. Not the exact one, mind you, because privacy, of course, but within some kilometers or so, so that the network may use that position as the location to start paging the UE. Maybe I forgot to mention, I think so, but the reason it's important to track UEs in mobile networks is that you want to be able to call them or to transmit data to them when they are not requesting something from you. So for example, when I just have my phone in my pocket and I'm take the train to another city in Denmark, Aarhus, a few hundred kilometers away, then my father would still like to be able to call me.
Yeah.
So he would only be able to do that because the network tracks where the UE is in a rough manner.
Yeah. So they're like, they know you're in the area, so they're going to be able to pass the message
exactly.
across.
And terrestrially, you know which base station that I was accessing last.
Yeah.
So you can call around those base stations, but in the satellite case, you don't know which, or it doesn't matter which satellite I accessed last. If you have moving satellites, if you have geo satellites, or you have moving satellites with cells that are fixed, beams that are fixed on the ground.
Yeah.
If you're in that case, so you have beams that are fixed on the ground, it's the same as terrestrial.
Yeah.
But if they're moving, you have all these new adaptations or new challenges to overcome.
Yeah.
Which can all be overcome. It's not a big deal. It's just a new paradigm.
Yeah. New cases.
Yes. Release 18 features. Network verified UE location. So as we just discussed, the UE location can be reported by the UE. But who is to say that the UE is not malicious? Normally it wouldn't be, but could be for some reason they are trying to spoof their location or something.
Smart question. Yeah.
Well, could be. So there's a feature now for confirming the UE location from the network side, doing measurements on the NodeB. Then you have mobility enhancements, TN NTN mobility, very significantly. which allows TN cells to broadcast information about NTN cells. So you might imagine TN cells on the edge of the TN coverage could be in harbor cities, or it could be close to deserts, or whatever is the case. Then you have the TN cells starting to give information to the UEs, the cell phones, whatever, that there are these NTN satellites which are flying on these paths. So when the UE moves out of coverage of the TN network, it can jump onto the NTN.
Mm-hmm. Yeah.
And then you also have the reverse case, of course, where when you're in an NTN network, there will be information about available TN networks which are nearby. So if you're going to leave or if you're going to go into an area where the TN coverage is good, for the ecosystem as a whole and for that particular UE, it's better to be on the TN network. You have a better service on TN. That's just a fact.
Yeah.
But
different conditions.
Exactly. Different use cases and so on. Then there are coverage enhancements. So a little tweaking of the PHY, giving more repetitions to the PUC, the control channel. And then bands and extension-wise, spectrum-wise, the 30 megahertz channel bandwidth for NTN NR has been defined. And then there's an extension of the spectrum in the L and S bands.
Okay.
So that is coming pretty soon.
Exactly. Remembering, as you said, like release 18, not finished yet.
The features are just about finished, I would say.
Okay.
But then after they finish the features, they have to do some practical coding for the standards, for the specifications, and then it really freezes. Like it's really finished this summer, I believe.
All right. Nice.
Release 19. There are different topics that have been talked about in the industry, and I listed some of them here. So on the physical level, so RAN 1, you have coverage enhancements, but for the downlink. Remember, release 18 put coverage enhancements for the uplink or repetitions per book. And then you have robust paging notification alert. Maybe this will be a part of the work for release 19. Uplink capacity enhancements. RAN 2, so on the higher layers, a little more into the control. There are mobility enhancements. There's enhanced GNSS operation. This has to do with the GNSS of the UEs might not always be accurate, always working. So if it doesn't work, we still want to have some sort of operation, at least for a few seconds. And then, support of broadcasting, which is a very well-known satellite use case, like satellite TV, weather, so on. Regenerative architecture is also a big theme or a big thing. As I said, the transparent architecture is the only one that has been standardized. But with this work item, there would be a look into the different splits that you can do of the protocol stack for regenerative. So it's a bit further than the conclusion we have made, where you can put all of the base station there. It's putting parts of the base station on the satellite. RAN 4. This is more into the spectrum and radio resource management part. Support for the reduced capability UE in NR. This is the cheaper, I wouldn't say IoT, but maybe IoT plus UE, which a lot of companies would like to see support for in NR NTN. There's, of course, enhancements to the spectrum, coverage enhancements, and then there is on the testing part for UEs, conformance testing for UEs in NTN. Right now, it's being done without emulating the channels. So there is a proposal to go back to this conformance testing in release 19 and looking into defining conformance tests where you need test equipment to emulate the orbital mechanics of the satellites for all of the tests.
Yeah.
Because they have been simplified for now.
All right, interesting. A lot to come.
Definitely.
Yeah. All right. So after all the background information, all the technical, let's say, advancements of that we need to go through 5G new radio NTN, you probably have the answer. Where are we at with 5G new radio? This is just to give an overview because it's an obvious question, I imagine. So we are at the first stages of developing our own 5G new radio software. As it is our expertise, we are developing the layer 1 of 5G new radio, and we are having some discussions with some possible partners for the other layers, and also so we are able to offer the full NodeB solution. So if you are interested in having a conversation with us about that, reach out to me. I can put our team together. We can have an initial talk about that as well. It will be my pleasure. So what can you do now, let's say, in terms of taking the first steps, right, into 5G new radio? As Renee said, there's a lot going on for years and for some time more in specifying the standards, right? So what can you do now? So what is ready to be done now is you can get ready before the technology, the market adapts to adopt the technology. So let's say before it gets deployed into NTN systems, and then before as well, the market actually starts, becomes standardized as a whole. So you can have already a very thorough look into your own system and have all kinds of estimations of how your system will perform and will react in many different case scenarios. So you can, prepare, build a business case if you want to do so, and prepare your roadmap, let's say. So when the time comes, you are ready to already, take a step into the direction you actually want, you desire. So in the meantime, as well, together with making your roadmap and validating it, you can also design it already. Your current system, make the adaptations that it needs, but also to your future solutions that you decide to take based on 3GPP. So this is something that if you want to have a talk, you want to have a look into specific things in your system, you can also reach out to me, also to Renee. We can set up a conversation about that, so we can look at your own specific case and maybe have a longer conversation about that to get your system up to date and everything ready. So yeah, as I mentioned, so when it's time, you can confidently make a move, take the first step, and deploy your services and your solutions and all that. So yeah, I think, yeah, it was a
we check the question and answers.
yes. Let's have a look into.
Can I have a few minutes?
Yeah.
Went a little bit over time with the presentation. That's probably on me.
I talk a lot too. So when should we expect the NTN MBB services to be commercially available in scale? So if I understood correctly, meaning like 5G new radio NTN services available out there, that's a bit of a difficult question to ask because, as we saw, there's a lot of things to be done yet that we're doing. And also, there are many different parts, many different key players that we need to all play together and sing the same song, let's say. So it might take a couple of years, but for our own vision as Gatehouse Satcom, we're gonna get ready to, commercially deploy the technology in around, let's say, 3 years. But it's it's not up to us so much to affirm when it will actually be fully out there, in the market.
If I could add to it for NTN IoT, so the MMTC part, you might expect commercial services to be launching fully in 24-25. And then NR NTN, which requires more spectrum, more everything, as you said, there are a few more things going into it. I would put that +1 on both years. So what is that? 26, 27 to see fully fledged solutions. And then, of course, we are moving into 6G territory for 2030 at that point. But I expect the NR NTN services to be around for quite a few years.
Nice. All right. What do you think about this one, Renee?
What's the advantage of regenerative architecture? Well, there are several advantages. The first one is that the latency is reduced on the NR interface. So every time you're exchanging information on these lower layers of the entire NR protocol stack, you will do it very fast. Then the flip side, of course, is that the propagation towards the core network for your next generation access protocol link on the feeder link will have an increased propagation delay, and the messaging here is much less though than what you have on the radio link.
Yeah.
So that's also why there's going to be a SW release 19 now. Because the way that you split the NodeB, putting all of it or some of it onto the satellite access node, is going to determine the performance increase you can see from doing that. And then, of course, there are many other things, such as you not being dependent on a gateway, which could enable store and forward functionality. You could, for instance, also foresee maybe a case where one UE or two UE signs range of the same satellite, and then they are able to make the call through the satellite to the other UE. So the satellite would access the ground network to verify billing information, authenticate the UEs, and so on. But once the connection was running, maybe it would just be a loop through a regenerative satellite. So there are many functions that could come only with a regenerative architecture.
Yeah.
But just putting the regenerative architecture without new functions, of course, the thing is going to be performance, latency, throughput.
All right. Many different things. Just a second, everyone.
Many questions.
Yeah.
Many good ones. Let's see.
What about this one?
In case of transparent sand, which air interface protocols will follow for communication between UE and satellite. So if I understand the question correctly, it is to the service link between the UE or your cell phone and the satellite access node. What will be the air interface? The air interface will be NR NTN. And I'm not sure if that's the question. In case of transparency, in which air interface protocols will follow? Okay. So maybe the question here is which air interface comes after the communication between the UE and satellite. Here the answer is it could be pretty much anything. So in one case, you have a UE transmitting via NR NTN air interface to the satellite, and the satellite is just mirroring the very same signal to a gateway or to a ground station on the ground. So there you have NR up in the service link and you have NR down in the feeder link. That's one way to do that, but you could also envision having a satellite that would sample the IQ signals of the UE to satellite interface, having sampled those IQ signals, somehow encapsulate them into packets and then transmit using another technology on the feeder link to the ground station. That's a perfectly viable option also. And I would still qualify that as a transparent satellite access node, at least in terms of the 3GPP architecture, because you will still need to put the NTA common delay, for example.
All right. Awesome. What do you think about this one?
I'm not sure what's being referred to also. So
yeah, so maybe we can take this one.
We'll take that one offline. Yes. Yeah. With Ku-band support in release 19, can we assume higher throughput for eMBB compared to what you showed initially, 70/2 megabits? Yes, I would expect so, but not because of the Ku-band support. So a couple of things. The Ku-band support will also come with the VSAT use case, because to achieve a link that is sufficient, it will not be direct to device as we know it for the lower bands from release 17. It will have to be large dish antennas or smaller dish antennas, smaller, larger, but high gain antennas. The Ku-band has more bandwidth, yes, but what will bring higher rates will not be just going to a higher frequency. It will be achieving a higher SNR from the high gain antennas, and it will be having a larger channel bandwidth. And the channel bandwidth for NR NTN is 5, 10, 15, 20, I think 25, and then 30 is coming. So if we define even a wider channel bandwidth, yes, you can expect that you will get even higher bandwidth, but otherwise this is it. And I will say also the 70/2 megabit per second is the required bandwidth. It's not the maximum achievable bandwidth or the in any way achievable bandwidth. It's a requirement.
Okay.
So if a system that you roll out cannot achieve this, it's not a 5G satellite system.
Okay, it's yeah, something else.
Yeah.
Okay, I think we have time for one more question because I'm so sorry we ran out of time a little bit, but we're gonna get to all of them for email. Yeah.
Okay. Thanks for the presentation. What are your thoughts about the need of new functional splits for regenerative architecture in Release 19? Would a LEO regenerative satellite be able to implement a payload with a full DU, considering it may need to serve many beams? Yes, of course. Here the answer is it depends, and as with so much in engineering, so typically LEO satellites are not very big, but I would argue that today even a small set can have considerable computing power. And putting a part of the NodeB, for example, a DU, which is just the lower layers of the stack. So the file layer, maybe a bit of the MAC, depending on how you split it, higher, lower MAC. That requires less computation than having the entire stack on board, of course. So in fact, having these functional splits would make it easier computation-wise to put parts of the NodeB on board. And with regards to having many beams, I would say it's definitely possible with FPGAs and application-specific ICs to have so much gain that you can do it in LEO. So that's my little longer hesitant answer. To make it shorter, I would say yes, it would be possible to do in LEO to have a full DU, even if you have to serve relatively many beams. I would imagine in LEO, though, the number of beams is somewhat limited.
All right, perfect. I think, yeah, I'm very happy. We got many good questions, but we also had a very good presentation. Thank you, Renee, for the entire answers and the presentation. Also, my questions during your presentation. Thank you. And yeah, I want to thank you for your time as well, for being here with us. Yeah, and I want to, continue the conversation with us, with you and us afterwards. If you wish to, you can always reach out. We'll be happy to hear from you. And yeah, that's it then. Yeah, we'll see you in the next webinar. Okay, bye, have a good day.
Bye bye.